Welcome to today's webinar with the title The World of Embedded Components in Printed Circuit Boards, Part 2, Layout and Applications. The speaker of today's webinar is Mr. Jürgen Wolf, Head of Advanced Solution Center. And now I wish you lots of fun and new information.
Thank you, Andreas, for your kind introduction. I don't know if you want to leave your webcam on or if you close it. I will start with the presentation itself. So first of all, let me give you a short introduction to my person itself. So as Andreas said, I'm the head of the Advanced Solution Center here at Würth Elektronik. I'm with Würth Elektronik since 2008, so it's already 13 years, quite a lot. And in my function as head of the Advanced Solution Center, I'm responsible basically for all the technologies above our standards, so above the multi-layer HDI rigid flex boards. So for example, for embedding, but as well, for example, for the stretch flex technology, where we have stretchable printed circuit boards in manufacturing. I gave a webinar about this technology in January, and I will have a second part where I explain the stretchable printed circuit boards in May. So you are welcome to join these webinars as well if you're interested in stretchable printed circuit boards. About the topic today, I will first give you a short summary of part 1 from December. Then we will have a look into the EDA tools and we'll talk about their capabilities, why they or how they offer to handle embedded components during layouting. Then we will go directly into the layout and see what you have to do and how to design a PCB with embedded components. And in the end of today's webinar, I will give you some short application examples. There are, since we do this several years now, for sure quite a lot, but due to time and so on, I will just give you 2 or 3 basic application examples. So what did I show you in part 1? So we were talking about how embedded components is being realized. I showed you the basics about our 3 technologies, which we can offer here at Würth Elektronik, which would be either embedding components into the PCB and contact them by microwires, or assemble components in a solder process onto inner layer cores and embed them. And the third technology is the flip chip technology, where we use bumped bare dies and flip chip mount them onto inner layer cores by the usage of an ACA adhesive. If you want to have more details about these technologies, please go back to part 1 of the webinar in our archive and have a look on these technologies in detail. As a second reminder, we were talking about the advantages and benefits of embedded components, that you can have miniaturization by either space savings of assembly area on the outer layers by moving components to the inner layers, or that you could create your own packages, your own system in packages, your own modules on the base of embedding. Then we were talking about performance and functions, short signal paths, protection against plagiarism, and we were talking about the reliability of these build-ups. For example, when it comes to thermal management, that you could connect components directly with copper on top and bottom, for example, so that the heat can spread out into the area and can go directly in short paths to the outer layer of the component, so that you have a direct copper heat and electrical connection. But let's move on to the layout part. And before we start with the EDA tools, I have a short question to you. And my question would be, which EDA software do you use in your company? And please, we do not, normally we open a poll from GoToWebinar where you can just click the different answers. Unfortunately, there are so many answers out there and so many software tools that the tool is not capable of handling all. So I would like you to insert your answers into the question section of GoToWebinar. And if you ask yourself, why do they want to know this? Well, this is pretty easy. It helps us because we are in discussion with several of these companies you see here in this list to get them to support embedded technology as well, embedding of components, because it doesn't help us if we offer the technology, but you are not able to create PCBs or to create a layout and a design for PCBs where you can use this technology. And therefore, we talk to different companies already. We have a collaboration, for example, with Altium, where I show customers how this can be realized with Altium, how components are being created. And this is something, for example, what I show you today. We are in talks with Cadence. We want to start, for example, with Mentor, now Siemens, and so on. But for us to give us a more profound base, it's really easy if you tell me what are you using, and then we can see if there is something which you use quite often and which we do not have on our screen yet. So Andreas, how is the answer function doing?
It's going well. I think we're getting more and more answers. So main tool seems to be Altium Designer, but as well as CADStar, CircuitMind, KeyCAD pads. So these are the chosen EDA tools by now. So maybe we need another 10 seconds, but that works fine actually.
Great. So thank you already for your answers. Unfortunately, we cannot sum it up as we usually do with the poll, since we just placed them into the question section. But we will internally sum them up and see what is your favorite tools and if we have to contact one or the other EDA manufacturer. So let's move on. Thank you for your answers, and we will have a look on what we already know. So we know that Altium Designer, Allegro from Cadence with the miniaturization option offer the capability to create boards with embedded components, as well as Expedition from Siemens EDA, formerly known as Mentor. They renamed themselves beginning of this year. Then we have Suken with the CR8000 package and Pulsonics. There might be other tools which offer this as well, but those 5 are the ones we already know, where we know that they have some certain capability to move components, for example, onto inner layers. There could always be the option that you can create a board with other tools as well, but then you have probably strong limitations or need to find workarounds where how you can move layers and components and so on. So we would have to talk about the possibilities when it comes to the point that you are not able to use one of these 5 tools. What does these 5 tools make them different to other tools? Well, first of all, you see here a standard multi-layer PCB where we have the components on top and on bottom. The mentioned tools offer the capability to move components to the inner layer. This is either, as you see here, that you create cavities and place the components from the outside onto these mentioned inner layers so that you can move the footprint onto the inner layer, or in the second stage that you really can define that the components sit on inner layer, but not only they sit on the inner layers and are assembled from the outside, but you decide the orientation, if they sit above or below a specific layer, or if they sit above or below a specific core. And let me show you how this is being realized in those tools. And by using the example of Cadence Allegro, we see here in the embedded layer setup that you, for example, can decide the orientation of the components. You see here the status body down, which means that for layer 5, a component is sitting directly underneath this layer 5. Then in Allegro, you can decide if protruding of adjacent layers is allowed or not. So if this component sticks through this layer, and if you allow this, and you can define the contact methods here in the attachment method. A direct attach in Cadence Allegro would correspond to our microwire embedding process, and the indirect attach corresponds to the solder embedding. The placement of the components then you can see here is only possible onto the layers which you allow. So if you have a 6-layer layup and you allow top, bottom, and layer 3, you only can place the component onto layer 3, and the other layers are forbidden to place components onto. And depending on the capability of the tool, you get a very good DFA support with complex rules, for example, distances in X, Y, and Z axis. Especially Cadence here, Allegro has the possibility to do a Z axis design rule check where you check if the height of the component fits into your layer stack or if you collide with one or another layer, basically. Other tools maybe do not have this, but I will show you later in an example with Altium Designer what you can do then if this really complex distance rules do not apply to or cannot be applied in your tool. So let's go directly to the layout questions. First of all, when you start with a layout, you have to create your components in the library. The components which you're using for embedding basically are created in the library like any other of your components which you're using for the outer layer assembly. But we would recommend to not use the same components for outer layer assembly as you would use for the embedding, so the components which are assembled on the inner layers, because it is often required that we have some additional information in the component library already. This additional information is, for example, information for the solder mask of the inner layers. As far as I know, none of the mentioned 5 tools is yet capable to create an automated inner layer solder mask and inner layer paste data. So you need to have an additional information here, and how you do this I will show later. And I would require a specific component outline. The specific component outline, for example, is needed for design rule checking, and we will see this later on as well. What is really important is the height of the component as a separate parameter in your library, so that, for example, you can give us afterwards a BOM of your components with the heights of the components mentioned in the BOM. Then we can do a double check if the height of the component really fits into the agreed stack up, or if there is an issue with the height of the component that it might protrude either a layer or protrude outside of the board, that it's not inside the board anymore because it's too thick. And an embedded component actually becomes an embedded component when it's moved into the inner layout of the layout. And you see this here as an example in Altium Designer. Here's the Properties tab of Altium Designer. And when we look at this small resistor here, in that case, we move it from the top layer. I call it VS for the German Vorderseite, but it's the top layer, and I moved it to the layer 3. And you see that the component moves down in the stack up and is shown here on layer 3. So then it's an embedded component, but it's created in the library, as I said, as a first footprint on top layer, for example, and it's then later on moved during the layout phase to the desired layer in the stack up. I would now like to show you the whole thing using Altium Designer 21 as an example. We start here in the 3D view, and to move a component on different layers, I would like to switch to the 2D mode and open the property tabs of the component that I want to move in the layer stack up. Currently, this component is on top layer. Altium offers me layer 4 and the bottom layer as additional assembly layers. But why only these 2 layers? I will show you later. I now move the component to layer 4. And as you can see in the 2D view, the color of the pads has changed according to the color definition of the layers. If we now switch back to 3D mode, we will see that the component has been moved down into the PCB build-up. So let's switch back to the presentation. When we look a little bit more in detail to these additional information, as I already said, some tools are not capable of providing solder resistant paste data for the inner layers, and therefore we need to find a workaround. And this workaround is that we create, for example, additional mechanical layers for solder mask and solder paste data for the inner layer. And when you prepare the data for manufacturing, when you do your output, that you send us these additional mechanical layers so that we can match them to the assembled inner layer. And here you see the difference, why I ask you to please use a separate component in your library for embedding. If you would do this on your standard component and would afterwards create your output, then the outer layer components would give us the same additional information as the embedded components, and we would have a mix-up, and we couldn't distinguish between, is this now a solder mask for the inner or for the outer layer? So if this is only information being given for the embedded components, then we can 100% decide to which component this belongs to. And a short side note and a reminder of part one. We are using solder mask and solder stop frames on the inner layers, so we are not using fully covering solder mask on the inner layers. And you can either send us the information for this as designed positively in your design so that you really show those solder mask frames, or you do it and create the clearances as negative, as you would normally do, or the tools normally do on the outer layers, and we will convert them into these frames. So we have created scripts which do these automatically. The only thing you have to do is you have to document it accordingly so that when we manufacture the board, the inner layer looks like the picture on the right, that we only have these solder frames surrounding the pads, which need to be soldered, and all the remaining area is without solder resist. The next thing I mentioned was the component outline, this specific outline, as I called it 2 slides ago or 3 slides ago. On the one hand, this component outline serves us to create routing programs, for example, and to define those pockets or cutouts, what we need for the components. If you remember part one, all the components are being placed into what we call the virtual cavities or cutouts, so that during lamination they are not being destroyed. And these cavities and cutouts, they will be filled with the resin from the prepregs which we use in the layer stack, so that their components are completely embedded by resin. But we are also using this for design rule checking, for example, to avoid that vias are being drilled through components. We had this quite a few years ago in one example. Even due to a double check, we oversaw one via going through a component. And here you can imagine this via destroyed, on the one hand, the component, and therefore destroyed the whole application. A lot of money has been spent for nothing, and we want to avoid that. And to do an automated design rule check, we would like you to define the outline not only as a contour line, but as a filled area, as you can see here. And with this filled area, we can check if a wire is running through this filled area, if we have touching areas, and then can see if a wire is correctly being placed or if we have a problem here. If we only have the contour line, this is not so easy to do, and therefore if you fill this area, this is much easier for us. And again, I am using Altium Designer as an example, and I would like to demonstrate the additional mechanical layers. I have already opened here the PCB library for this purpose, and the component was first defined in the library with its footprint on the top layer, as I mentioned, and it only turns into embedding component when it's being defined to the actual layer in the used layer stack onto the corresponding layer in the layout phase. However, you can see from this example that I have added an additional mechanical layer for each of the topics I have just mentioned. So we have the solder mask definition as clearance drawn in a negative here. Then we have the paste data matching the pads, as you see here. And last but not least, we have the component outline with these filled areas. Here you can see this. So we switch back. Okay, so let's have a look onto these cutouts or pockets or cavities, however you would like to call them. We have different definitions for this depending on the used technology. For example, for the solder embedding technology, the height of this cutouts is composed of 3 different things. So first, it's the height of the component. And here I would like to use, or I would like you to use the maximum tolerance in the data sheet, because for sure, we have to definitely make sure that the component fits into the stack up. And therefore, please use the maximum tolerance for this calculation. Then we have the solder standoff, which is approximately between 25 and 50 microns in our process, depending on the components and on the layout and on the footprint. And we need an additional space or distance above the component, between the component and the next either copper layer or the next core material or whatever it is, of around 70 to 150 microns. And you can sum these 3 points up and create, for example, here in Altium again, a cavity height definition in the properties tab for this specific component in the library. And again, in the case of Altium, Altium has the capability to create what they call a managed stack. So when you introduce this cavity in the library and you place the component into your layout and move it down onto here, in that case, layer 4, Altium creates a managed stack here called the stack 0, where the cavity actually is being shown, and you see which parts of the stack are being affected by this cavity. I have a very detailed stack tab here where I in detail introduced all the prepregs being involved. Often you only become, or you get from us, the isolation distances between those core layers. So you do not probably get it that detailed, but you still see, is this kind of distance being affected, or is the component protruding into, for example, here, what they call the layer 14, into this core with a thickness of 360 microns. As you see here, this core with the 360 micron is being affected. And if we would have a layout, in this case, it's only a filling core, but if we would have a layout here, so a copper layer on top and a bottom, you would have to take care that there is no actual copper structure in this part, because we would cut it out to create enough space for the component that it's not being destroyed when we do the lamination. Then when you switch to 3D mode in Altium, you really actually can see this kind of cavity when you do a cross-sectioning cross-cut here in your layout. And this can be used either by us or by you as a layouter to check whether the desired component fits into your layer stack or not, and if the heights correspond to your desired stack up. And let's come to the stack up itself. So during the project phase, when we were analyzing together with you your bill of materials, the BOM, and defined the components which can be used for the embedding of them, we provide you with a layer stack up. And this layer stack up has to be implemented by you into your EDA tool up so far. We do not yet offer, for example, that we directly send you the Altium-based tool-specific stack up. If you would like to have us do this, then please put a note into the question section of GoToWebinar if you would like us to provide you not the PDF stack up, but the tool specific stack up. And please note which tool you're using if you do not already have noted this during my first question. In the layer stack up itself, you see that we give you information about the component location as well as the orientation. So if, like in the picture shown here, it sits above this core, which consists of layer 3 and layer 4. We give you as well the possible layer relationships, either giving as via, so a top to bottom via, or a buried via, or a blind via, and we give you the impedance information if you desire to have, for example, a specific impedance between layer 2 and layer 3, or whatever you want to have. And again, let's switch to Altium one more time. To demonstrate the implementation of the layer stack up in the ECAD tool and the components, we see this here as part of Altium Designer, the Stack Up Manager. And I can show you in the Stack Up Manager why only layer 4 is accepted as the inner layer for embedded components. At the moment, only this layer allows a component to be assembled in the orientation settings. In this case, only top assembly on the core of layer 4 and layer 5 is being allowed. I would like now to enable bottom placement on layer 3 as well. Until now, placement has not yet been enabled here due to the not allowed orientation. So we change this to a bottom orientation and save this stack up and close it. If we now look at the layer settings of the already moved component, we see that layer 3 now has also been made available where you can move the component. So the component is now virtual sitting underneath layer 3 when we switch to the 3D mode. You see this here. To demonstrate the difference to the component cutout, I will open the PCB library. And I have already copied the just move component in the library and additionally inserted the component cutout as a cavity on a mechanical layer. And I have calculated the cavity height according to the data sheet as described before. Here in that case, it's 1.12 millimeter. If we now move this component to layer 4 in 2D mode, so I switch back, go to 2D mode, move it to layer 4. We can see the cavity in the 3D mode because I intentionally placed the component directly at the edge of the PCB. If you have placed the layer stack table in the layout, you can already see that the cavity has been added as another stack. So we switch to 2D. But since Altium Designer does not perform a Z-axis design rule set, unlike other tools, you can at least here check very well whether the part fits into your layer stack. Unfortunately, to do this, the layer stack table managed by Altium must be forced to update itself by making a small change. But after that, you will see the additional stack with the Z-axis clearance, as you can see here in that case for this second stack. So let's switch back. And let's talk about the placement of components. So again, a brief reminder of part 1, and I already said this in this webinar, the components are completely embedded by the resin of the prepregs which we use in the stack up. But to do this and to get to that point, it is not allowed to use the entire area of the inner layer and to occupy it with as much as components as the tool would provide and as you can. We need to have around 40% occupation, not more, on the inner layers. And best would be to group the components as you see it here. And this grouping helps different purposes. On the one hand, it serves the fact that we can make sure that all these areas are being filled with resin from the prepregs. And on the other hand, we do not have that much of effort when we create the mechanical programs for the routing or the drilling to create those cutouts for this virtual cavity. So based on this information, you see here, we create then these programs and can start and use them in the manufacturing. So let's move on to some application examples. If you have more questions about layouting, if there is questions which have not yet been answered, so please put them into the question section. We will answer them afterwards. Or if after the webinar you have more detailed questions, do not hesitate to contact us directly after the webinar. So let's look on the first application, and I've taken one from the automotive sector. This is an embedded gallium nitride MOSFET for a half-bridge switching cell. And you can see here a micro-sectioning of the printed circuit board. It's a 4-layer built-up with microwires connecting the components. So we have a microwire embedding setup here. This is a work being done together with a high school or university here in Germany, and for an automotive end customer, this is the pre-evaluation phase. So what they did, for example, is they double-checked the embedded build-up with a surface mount build-up, and we are checking, for example, the junction temperatures, how these behave. And you can already see in the simulation that we have a much more uniform heat distribution, and the performance is really, really good. What was interesting is that we didn't fully go to what the technology is being capable of. So we could even create a much better performance. We still can, in that build-up, double the number of microwires connecting the component, so that we even would get a much better effect. The only question is, how many more wires are you spending? Because this again goes into the cost calculation. The more wires you make, the more costly it gets. So you always need to find a trade-off between cost and performance. If you want to have a more detailed look into this, this has been published by our customer, Mr. Deckand. You see the source here on the top right. So you can look up this paper and have a little bit more detailed insight into this. Afterwards, for the next part of this project phase, we did an optimization of the build-up, and you can see here that the backside microwires contacting the component have been reduced in size so that we have less distance for the heat to get out of the systems, not the systems, so that we have an even better performance here in that case as well. Next example I want to show you is one where we really tried to push to the highest reliability requirements which are possible and capable for the technology. To show you what I mean with very high reliability requirements, in this application, the operating temperature can reach maximum 200 degrees Celsius. We need to be cycle proof in the temperature cycling, at least 1000 cycles from minus 55 degrees Celsius up to 225 degrees Celsius. And this is really, really, really high, even for automotive standard, where you normally go up to, for example, 150 degrees Celsius. So we are much higher here. It should have been as small as possible, but still, it should be able to use it in an injection molding process. Why do I mention this? Because these two last points, well, they conflict with each other. The smaller it gets, the more the module might be affected by the pressures being used in the injection molding. And therefore, we needed to find a way in a build-up how to still make it very small, but find a way that it's not being bent or distorted during the injection molding. Why all these different requirements? Well, this sensor directly sits in the engine compartment, very close to the turbo. And there you can see where this high temperatures come from. So what we did is we created a module with 3 different components inside. The stack up you can see here, it was an overall thickness of less than 300 microns. To get to this performance, we were using a high temperature substrate material, which has a TG over 240 degrees Celsius. And by the combination of this high temperature substrate together with our microwire contacting embedding technology, we could fit to those requirements. You see here on the bottom left, the module which we created. So you see the wires which contact the outer world in the molding part, and you see wires going to the inside, and the components are being hidden and contacted with microwires. And on the right side, you now see a micro section after the 1000 cycles in the temperature cycling from minus 55 to 25 degree, and you see that there are no cracks and no other failures. The only thing what you might see is that the material, the dielectric itself, darkened a little bit, so it's not that reddish brownish as you see in the bottom left. It's more dark brown when you look at on the real module. And this you can see here in this cross section as well, that the material is rather dark compared than it would look like afterwards. But that's the only thing what we saw during the cycling, that the material darkens, but all the other stuff, there were no errors here from an electrical or mechanical point of view. So let's move on to an example out of the medical technology. It's an embedding Asic, a radio module for implants. It's being created by Microsemi, or we would have to say microchip nowadays, because Microsemi has been bought up by Microchip. But this is a component which you could buy out on the market, and you can look up all the information in the internet about this component. And I just collected this information a little bit for you. So you see that Microsemi created an own module. They started with a standard SIP where all the components have been placed on the outer layer. And by taking this die, which you see on the left side in the middle of the board, and embedding the die into the PCB, they could shrink this module quite a bit. 70%, as you see here, from the overall area being used by the module, which is quite a lot, I would say. And when you look on how this is being done, you see here the 3D model where the embedded ASIC is being shown. And when you do the cross-sectioning of this model, then you directly see this die being solder assembled onto this inner layer core here in that case. And when you take a size comparison, since Microsemi or Microsemi, the company itself is, I think, placed in the US or Canada, I think Canada. Our counterpart is sitting in the UK. You see the size comparison with this one dime, that this is really a very, very small module now being used, and miniaturization is a basic need for the implant. So the smaller the module, the better for the implant size and the better for the wearer of the implant. So you've seen these examples and all the technology and the layout questions and answers. And in the end, I really, again, would like to ask you this short question. When you look back and review these two parts, what do you think about our embedding technology? And now, Andreas, I would like to switch you to the real poll function here. And I would like to answer you or answer me these questions. I have several options here. Yeah, you already have a concrete, a specific project idea, or yes, you say it's interesting, but it needs time to settle down and think about it. Or yes, I want to know more. Please share me more information. And the last thing, what I hope you do not answer, but please feel free to answer truly to that if this is nothing what you were expecting.
Okay, we've got 60% already. So we will wait another, let's say, 5 seconds roundabout. So your answers are really appreciated. Okay, so now let's close the poll and let's see the result.
So thank you for this. No one answered it wasn't what you were expecting. So I at least could fulfill that part that you got a first overview. I see that half of you find it interesting, but it needs to settle down, and half of you want to know more. And even already 10% of you already have a project idea, a specific project. So do not hesitate and contact me if you do not already have done this, and that we can talk about this and see how we can realize your idea into real hardware. Okay, so thank you for this, and thank you for your attention. We are at the end of this presentation. As I said, if you have more questions, we have the question and answer.